Hello again, everyone. Welcome to the second part of this lecture on residual stress. In the first part, how residual stresses can be developed at the macro scale was described. In this part, the types of residual stresses as defined by the length scale over which they equilibrate will be covered, along with their effect on degradation mechanisms. As previously detailed, there are three main mechanisms by which residual stresses develop. Mismatch of deformation rates of regions within a component can cause them, as can a misfit. Material with different thermal expansion coefficients can result in different contraction rates during cooling, which can result in a region larger than the surrounding material, can accommodate absent of stress. Finally, phase transformations can cause displacive stresses to form, exemplified by the martensitic transformation, which is shear-like, driven by a packing factor substantially changing between FCC to BCT structure. It is apparent that there are some of these sources that can operate on different length scales. Bulk plastic and thermal processes occur at all length scales, and the collective behavior of a transformation will cause far-field residual stresses. This gives rise to the need for classifying the length scale over which these stresses equilibrate and therefore affect engineering properties. There are three types of residual stress. The most prevalent ones you will likely encounter is type 1. These are continuum scale residual stresses which equilibrate over millimeters to even meters. However, there are another two types below this. Type 2, which equilibrate at the grain level for polycrystals. These are driven by texture, segregation, solid solution effects, amongst others. One level below this is at the nanometer scale, and these are type 3 and driven by dislocations, crystal faults such as vacancies, and so on. The collective behavior of this type 3 decides the behavior of type 2 over a longer length scale, and the same for moving from type 2 to type 1. Type 2 and 3 are not that important to consider from a practical engineering perspective, but they are when it comes to measuring type 1 stresses, as the type 2 and type 3 aspects can affect some techniques, such as diffraction with X-rays or neutrons. Measurement of type 1 stresses is often required as they can affect the performance and design of engineering systems. Let's start first with what happens to yield behavior. Remember that residual stresses are elastic in nature and self-balancing. What that means is that they will offset the yield stress in the regions where they apply. That means for a component containing residual stresses and subject to external loading, then there will be some regions which will require less loading to yield, those in residual tension, and some that require much more, those in residual compression. If we were to consider the component to have zero overall strain prior to loading, then the net effect would look like this: a significantly higher external stress to yield for the region that is in compression, while a significantly less for that which is in tension. This is the effect on yield, as demonstrated by equivalent stress-strain curves. Therefore, consideration of what and where residual stress can manifest is important to some critical engineering components, as they will not carry their design loads without yielding in the worst case, and be over-designed in the best case. The same is true for components subject to fatigue. A tensile residual stress acts and adds to any existing mean stress, pushing the mean stress higher. A compressive residual stress would do the opposite, pulling the mean stress down. This means that the tensile residual stress creates a more aggressive fatigue regime, pushing the load ratio R to be more positive. For a given amplitude or maximum stress, this will result in fewer cycles to failure. The opposite is true, as compression will push the load ratio to be more negative, increasing the number of cycles to failure for a given load. This is true for both materials which are initiation or propagation dominated. There will be less driving force to create a stress concentration and crack, and less loading that serves to open that crack. To illustrate this point a bit further, a tensile residual stress acts in concert with external loading, so any far-field stress surrounding a defect or flaw is raised to a much higher maximum stress. Note that the stress concentration factor does not change in this circumstance, but the maximum stress obtained does. This means that a tensile residual stress will increase the crack driving force, while compressive stresses will decrease or even suspend it. Therefore, if one can introduce compressive residual stress surrounding a potential stress riser, then the overall performance of the component will improve. For both components that are subject to fatigue and fracture, some industries will pursue secondary surface treatments to create these compressive stresses. For example, some turbine manufacturers will employ laser shock peening on their blades to improve their service lifetimes. There is another degradation mechanism that can be affected by residual stress, and that is corrosion. While corrosion mechanisms aren't covered here, they will be covered in later courses. Briefly, corrosion processes are electrochemical in nature, whereby either reduction or oxidation takes place. Stress corrosion cracking, or SCC for short, is a very complicated degradation mechanism, which requires a susceptible microstructure, a stress, and an environment that encourages corrosion to take place. To the right, I have two samples of cartridge brass, with the one on the left completely annealed so there is no residual stress, and to the right, one that is not. Let's see what happens when they're left in some mercury nitrate. Mercury immediately comes out of solution and deposits on the brass, encouraged by local anodes. The mercury then diffuses into the brass, causing significant embrittlement. After some time, axial cracks develop due to residual hoop stress. The result is fairly dramatic. As the cracks appear, they also accelerate as there is now a faster route for mercury to get into the brass. While the cartridge on the left has the same microstructure and has been exposed to the same environment, there is nothing to drive a crack. This is a bit of a parlor trick, but it does demonstrate what can happen in other corrosive environments with a susceptible microstructure. Let's now look at what kind of residual stress you can obtain in an engineering component. Here's a diagram of an actual component used during welding trials of a thick-section structural steel, SA533, used for nuclear reactor pressure vessels. The goal of making this component was to test out a welding protocol to ascertain the development of residual stress and microstructure obtained at the joint. In order to assess the residual stress developed after welding, it was cut carefully in half to release all of the stress in the longitudinal direction. After some fancy metrology and numerical analysis of the distortion stemming from the released residual stress, this was the resulting distribution. A big pocket of near-yield residual stress, some lesser tensile stresses, and again, this is all localized on the weld, which were balanced by compressive stresses on the outer edges and restraint. Running a pair of traces over this contour map, the one at the highest, trace 1, and trace 2, lowest in the weld, it looks like this. So a yield for trace 1 and about half of that lower down for trace 2. Note that this limited trace does not show equilibrium. This is because they're balanced much further away from the weld. However, it can be observed that they are tending to compression about 100 millimeters away from the weld center line. So clearly this is a component which requires remediation, a method for reducing residual stress. This can be done either by changing the primary process or follow-on process such as heat treatment. Post-weld heat treatments are often employed both for residual stress reduction as well as microstructural refinement. I'd like to highlight that this is an example that's not suitable for service because of the high levels of tensile residual stress. Programs for manufacturing of high-value infrastructure will often require multiple assessments of residual stress and iterations of both the process and remediation to determine the most effective route. So in this part of the lecture, it's been shown that residual stresses are generally superimposed on those stresses that arise when a material is in service. Residual stresses can either be beneficial or detrimental to the integrity of engineering components. Surface treatment techniques can be used to produce compressive residual stresses at the surface of components that are subject to fatigue loading or prone to stress corrosion cracking. Other abatement techniques include post-weld heat treatments, but these need to be carefully applied in conjunction with modifications to the originating process in order to be the most effective. Until next time.